Let's talk about dimensional analysis. Dimensional analysis is a technique of determining if an equation makes any sense or not. It's a very quick and dirty look at it. It's not going to be able to detect if there's a constant off or not. But just give an example here. I know that the SI unit for speed, let's make it velocity. The SI unit for velocity is meters per second. The SI unit for displacement is meters, and the acceleration SI unit for acceleration is meters per second squared, and time, the SI unit for time is seconds. And so if I have the equation of v squared equals vi squared plus 2a dot delta x, is this even remotely viable given the units? Well, so when you're doing dimensional analysis, you just plug units in here. So I'm going to do specific units, and I'm going to talk about the more generic way of doing it. So this would be meters per second squared. Is that equal to meters per second squared plus 2 times meters per second squared times meters? Is that, so all we need to know is, looking at units here, or that 2 has no units, so that would actually go away. Well, if I need to add apples and apples. That's meters squared per second squared. And that is, well, meters times meters. I can always put anything over 1, so I have meters squared over second squared. And so on my right-hand side, I'm going to have meters squared per second squared. And on the left-hand side, I will have the same. So dimensionally, it works. What about delta x equals VIT plus 1/2 AT? I've seen this before. So is this valid? Let's go ahead and put the vector symbols in there. So that would be meters. So I expect that to be meters and that to be meters. So VIT, so this is meters per second times seconds, which is, well, the seconds would cancel out, and what I'm left with is meters. And over here, I have 1/2. Well, that has no units, so I'm not going to worry about that for dimensional analysis. And then I have meters per second squared times seconds, and so that's going to cancel out with one of those, and I'm left with meters per second. This is not a valid equation. Turned out that that should be squared in order for it to be valid. I know that momentum is mass times velocity. So change in momentum is force times time, technically average force times time. And so these are two equations, and let's just make sure that it is actually works. So momentum is mass times velocity. I know that the units of momentum must be the units of mass times the units of velocity, because that is a true statement right there. And so I'm just doing this in order to get units. And so this must be kilograms meters per second if we're dealing with SI units, or a kilogram meter per second. Now over here, my change in momentum will have the same units. So this is a kilogram meter per second. Both units for force in SI is a Newton, and the units for time is seconds. So the question is are these the same thing? I know that force is equal to mass times acceleration, and so my units here, newtons, must be equal to a kilogram times a meter per second squared, because those are the SI units for each of those. So now if I plug that into here, I have a kilogram meter per second on the left, and on the right, I have a kilogram meter per second squared times seconds. That's going to cancel out there, and yes, indeed, that at least passes the first level of scrutiny. All right, in 2001, a Swedish philosopher named Nick Bostrom wrote an article, Are You Living in Computer Simulation? It got published in 2003 in Philosophical Quarterly, volume 53, number 211, from pages 253 to 255. He published this, and as part of this paper, he included an equation. So each of these, how he got to this is not particularly important right now. What we're going to do is a dimensional analysis of this. So this is the fraction, well, let's get into the definitions of these things. So F sub sim is the fraction of all observers with human type experiences that live in simulations. It's a fraction. If we multiply it by 100%, we would have a percentage. Its unit is 1, or it is unitless. F sub p right here and here. It's a fraction of all human-level technology civilizations that survive to reach a post-human stage. Now, the fact that it's a fraction of one thing to have reached a particular point it is unitless, or it has a unit of 1. N bar is the average number of ancestor simulations run by post-human civilization. So the units of N bar, and by the way, the bar typically means average. The units of N bar is simulations. So there are 5 simulations, or 5 ancestor simulations, but I'm just going to shorten it down to simulations. So the units of N bar are simulations, and the units of H bar, average number of individuals that have lived in a civilization before it reaches a post-human stage. So it's the average number of individuals, and so its units are individuals. So there are 5 individuals, so individuals is the unit. And I've written it over here that the units of F sub sim is 1, the units of F sub p is 1, the units of N bar are simulations, and H bar is individuals. And I'm just went ahead and shortened that. Instead of simulations, I wrote S. Instead of individuals, I wrote I. So if we look at this equation here, that the units should be dimensionally correct. It should balance on both sides. And so this right here is just saying that the units of F sub sim is equal to the product of the units of the top divided by the product of those units plus the units of that. So dimensionally, when you are adding, you need to add things of common units here. So those units and those units, so the units of this combination here should be the same units as H bar. And so basically what I've written here, as well as the units of the denominator should equal the units of the numerator, so that they would cancel out to ultimately give us a unit of 1 here. So if putting it into using S again and I, we have 1 on the left-hand side. This is 1. This is the number of simulations. This is the number of individuals. And so our numerator has units of simulations times individuals. The denominator here, this is 1. This is simulations. This is individuals. And then plus this is individuals. So on the denominator, we have SI plus I. This does not work, because the denominator has to have the same units as the numerator, so that they would cancel out to give us 1 overall. Dimensionally, it doesn't work. So from my point of view, his paper had all sorts of flaws, but this one in particular was, to me, egregious. I think a lot of his assumptions were invalid. The numbers he came up with were specious at best. But this in itself, if he had done a dimensional analysis, he could have saved himself a little bit more trouble. One, he might have said, oh, this doesn't work. As it is, in 2015, he came out with a corrected this formula here, but it felt like he was just basically, he liked his conclusion, and so he forced it in order to match what he wanted it to say. But anyway, dimensional analysis would have saved some stuff. Or perhaps he did it on purpose so he could have another publication. When we were doing the dimensional analysis at the beginning of this video, I was looking at SI units only. So for length or distance, we have SI units of m. For mass, it's kilograms. For time, it's seconds. But typically when you're doing dimensional analysis, you aren't necessarily stuck in any particular unit system. These are international standards. It's a particular subset of the metric units. But generically, because there are other units of length, there's feet, there's centimeters, there's inches, there's yards, there's miles, there's parsecs, there's light years. There's a lot of them, so we can just generically use the capital L to represent length. Mass, we can just use a capital M, because there are other units of mass besides kilograms. There's also slugs. And then there's this thing called pound mass, which I'm never 100% sure what pound mass is. And then there is time, and so we can just use a capital T for time. So if we look at that, then velocity on the first page I said was meters per second, but it is just basically going generically L over T. For acceleration, it's meters per second squared in SI units, but for generically, it's L over T squared. So this way we have sort of a general all-purpose unit here to match it to whatever system you happen to be using. So if we look at that equation again here, this time with the correct square there, looking at units and generic units, this is displacement, which has the same units as distance or length, and so that would be L. And then we have L over T times T. And so T's would cancel out. And then we have something that's unitless. A is L over T squared, time squared is T squared, time squareds cancel out. And so I'm left with L L, which would add together to get you L. And so dimensionally it works. We can also look at the equation F equals ma. The units of F equal the units of m times the units of a. The units of mass generically are capital M. The units of acceleration generically are L over t squared. And so the units of force must be mL over t squared. And so this would be the generic base unit system here. And we have, and if you go to SI specifically, a Newton would be a kilogram meter per second squared if we just plug in the SI units. And that actually is true by definition. So we put the third line in there. This indicates by definition. Just another side note, sometimes you might see that written as Newtons with a triangle over the equal sign, kilogram meter per second squared. The difference is these are considered base units and this is considered a derived unit.